polynomial by Legendre and Gauss to consider large language models mimicking human brain, in which many neurons are connected and each of them can be activated or not activated depending on the task we are undertaking. And then based on existing data, build a function just by training, by optimizing the parameters so that this function is able to match the initial data to the final outputs. So the input to the output, the data to the labels, right, by means of this function. As I said yesterday also, we are not really interested on doing a very sophisticated interpolation, right? So we don't want to take a data set of trillion of points and then build a polynomial of, degree trillions passing through all these points. What we want is just to get the main trend of the data set so that it can generalize. And generalize means that whenever someone gives me a new input, I will be able to guess what the corresponding label is with high probability, right? So yesterday, for instance, Professor Zhao was talking about the softmax, that is precisely employed in order to allocate probability to the different possibilities on a learning task. Professor Zhao was also talking about sampling. I didn't mention this, but this is, of course, critical. Nowadays, when people think on artificial intelligence and machine learning, sometimes we have this naive perspective that, the problems I don't know how to solve using classical numerical analysis or partial differential equation, I will solve them with machine learning. Well, in order to, make machine learning successful, you need a good data set. So sampling is extremely important. So you will not recover information that is not included in your data set, right? So if in your data set there are only, 2 colors, you will hardly, recover all the diversity of colors of the rainbow, right? You need samples, sufficient samples in order to be able to reconstruct the whole density, probability density, and then be able to generalize well. So sampling is extremely important. Sampling, labeling is very important. And this is why all these successful endeavors, operations of machine learning are always developed not only by the mathematicians of the computer scientists, they have to be developed together with the experts in the field, right? If you are talking about, brain diseases, you have really to talk and work with the neuroscientists because they are the ones that can, out of different scans, tell you, what is, the pattern of a healthy brain and what is the pattern of a brain that has developed some specific diseases, right? And you know that sometimes, nowadays, that neurodegenerative diseases are more and more frequent, sometimes it's hard to make a good diagnosis because there are different possibilities, and then you need the best experts in order to determine whether it's A or it's B, right? Okay? Whether it's some kind of dementia, whether it's Alzheimer. So this needs the input from the best doctors. And this is a task that has to be done a priori. It's the pre-processing task in which the data set has to be well prepared by using proper sampling methodologies and also good labeling methodologies. Because as we said yesterday, if you don't have labels, you just have inputs, but you don't know the labels, you don't know where you are heading, basically the only thing you can do is apply a heuristic algorithm in the spirit of Lloyd that will split your data set into subsets, but this could be quite arbitrary and will not really contain information about the topic you are searching. Anyhow, so that was the general idea. It took many, many decades for these methodologies to be developed. Nowadays, they are in there. They are actually now on our pockets, thanks to supercomputing and the abundance of data on the internet. Okay. Now, still, from a mathematical perspective, as mathematical analysts, we can wonder why this works. And as I said, this is due to well-known density theorems. Density in the context of artificial intelligence and machine learning is called a universal approximation, right? And the first result of universal approximation is due to Norbert Wiener, as I said yesterday, take a Gaussian profile, and then let me translate it arbitrarily with BJs. Let me amplify it with the weights W. Let me choose K of them, K going to infinity, by strategically choosing the number of K, the B's and the W's. This linear combination of Gaussians, right, can approximate any function, say, in L2 of a compact set. And this was proved by Norbert Wiener. I think it's 33. I should check again. In Annals of Mathematics, Tauberian theorems. And this, as I said yesterday, is a conclusion of a consequence of the use of the Fourier transform, and more precisely of the fact that the Fourier transform of the Gaussian G never vanishes, right? So basically the idea is that you write F as the inverse Fourier transform of the Fourier transform, and then you use a quadrature formula for this inverse Fourier transform. It's an integral, you make it become a series. But in this process, you really you have to divide by the Fourier transform of the basis function G. So as I said yesterday, it took more than 50 years to get to this point where people, were able to replace the Gaussian by this sigmoid. And experts wanted to replace this activation function by the sigmoid because this sigmoid mimics well the action of neurons of being either on or off. The theorem by Wiener could not be applied directly because the Fourier transform of the sigmoid is not is not positive everywhere. It changes sign. There are plenty of oscillations on the Fourier transform of the sigmoid, so you cannot apply Wiener's theorem or Wiener's proof. And then actually, in the paper by Sibenko, what he did was, enlarge the original ansatz by Wiener, that was simply like this, into this one below, in which, as you see, we have added one extra parameter A, which is scaling the variable X, right? So we move from this ansatz into this more general ansatz, and somehow, because of this more general ansatz, is that you can still prove the theorem of universal approximation. After this theorem by Sibenko, there has been a broad literature about how to enlarge this theorem by Sibenko. For instance, there is, I think, like 99 or so, there is a celebrated by Pincus, which basically says that this theorem, right, of universal approximation using this scaling drift and weights is in fact true for any activation function sigma, which is not a polynomial, right? So the proof is actually not very sophisticated, and but it is still, even if we don't, we will not present the proof here, it's good to think why not being a polynomial is important over here. So what will be the difficulty if I try to prove that this kind of linear combinations is dense if if sigma were a polynomial? Why it will not work? Why do you think it doesn't work for a polynomial? Well, take any polynomial, say a parabola. Assume we take a parabola here, sigma ax squared plus bx plus c, any parabola. Say x squared. Why x squared is not good? Well, because wherever I do, if sigma is a parabola, regardless how many times I add, and what values of b, a, and w I choose, each of these terms will be a quadratic polynomial. And when you add quadratic polynomials, I mean, you can make the addition very large, but it doesn't matter. You get a quadratic polynomial. So you see that if you choose as activation function sigma, a function that is a polynomial, you will never escape, the subspace of the polynomials of the same degree. And therefore, of course, this cannot be dense, right? So precisely in this result, the fact of being Gaussian or being sigmoidal is extremely important because, you are not confined to polynomial activation functions. So sigma or G, the basis function, the fundamental basis function, the atom that is used to generate all possible approximations in the context of machine learning and artificial intelligence is often called the activation function, right? So it's the function with which each of the nodes, each of the neurons is being activated. Okay, so keep in mind, from a mathematical perspective, you can get very, very far. The only thing you need to avoid is the fact that sigma is a polynomial, okay? But this was the initial, way in which mathematicians thought. I mean, that's a natural mathematical, perspective, right? You see a theorem and you say, oh, let me see how far I can extend it. But from a practical perspective, the theorem went in an opposite direction. People said, well, it's okay that you can generalize the theorem a lot, but in practice, we are not really interested on generalizations. We are rather interested on simplifying as much as possible the choice of the activation function. Why? Because this has to put in a big machine with many neurons, so the simpler, the better. And nowadays, the function that is more often used, very often used, in practical applications is this, so-called rectified linear unit. So the function x plus, which is very typical in partial differential equations. So for instance, is the function you use in order to prove the maximum principle for the Laplacian, the fact that applying positive forces leads to positive solutions. You normally take the positive part of the solution and integrate by parts. This function in this context is called ReLU, is the rectified linear unit. Okay, this is just a name. And this is somehow the simplest function that realizes this necessity of distinguishing 0 and 1, left and right. This, of course, you could take also a Heaviside function, right? You could take, a Heaviside function, but then this function will not be globally Lipschitz. ReLU is nicely globally Lipschitz. So to better, maybe some comments on the proof. So proof in the spirit of Sibenko, as I said, the proof of Wiener uses the representation through the Fourier transform. The proof of Sibenko is a bit different. So it employs Ham-Banner, right? Right? He says, basically the idea of Sibenko is assume that this set, the span of all these functions of neural networks, actually, this neural network architecture is often called the shallow neural network, right? Shallow, why? Because there is only one layer, right? It's not like in the previous architectures in which, I was considering rather more sophisticated here, right? So here I was considering more sophisticated architectures in which, the neurons were, accumulating over different layers and transferring information from layer to layer. So this is the case where the neural network is just one tall column, right? It's a static, it's an static ansatz. And this is called the shallow neural network. So the proof of Sivenko was rather to say, assume the span generated, the subspace generated by closure by all these shallow neural network realizations is not dense. If it is not dense, because of Ham-Banach, there is a function that is orthogonal to all of them, right? So if not dense, there exists H in L2, non-zero, so that H is orthogonal to all these sums. You say, well, if I am orthogonal to all the sums, in particular, I am orthogonal, I just take the case k equal 1, then this implies that H is orthogonal to all functions like this, right? Very good. Now, let me now think on the case where A goes to infinity. So I remind you yesterday, this is a scalar product. So here you have D parameters and B is a scalar. So what happens with this kind of sigmoid functions when this scaling parameter A goes to infinity? Well, when A goes to infinity, right, you are compressing the variable x. Therefore, this sigmoid function is becoming a Heaviside function, right? Either like this or like this, depending on the orientation of the sign of A and the location of B. So you see in 1D, at least in 1D to fix ideas, if H is orthogonal to all these shallow neural networks, H is going to be also orthogonal to all Heaviside functions. And what does it mean? It means then that H, then necessarily, H is such that, so it's orthogonal to any Heaviside function of the form like this. So this means that the integral of H is going to be 0 in any interval to the left of some point C and also to the right of any point C. And now I ask you, what do you think is the function H? So what is the function H? So that whenever you take the real line and you take any segment to the left, the integral of H to the left is 0. And anytime you take a segment to the right, the integral of H is also 0 to the right. So are there many functions so that whenever you take a segment to the left or to the right, the integral is equal to 0? Probably not, right? In fact, the only function doing this is the 0, 1. Why? Because, assume you have such a function on the real line and give me 1 point. I like to show that the H is equal to 0 on that point. How am I going to do that? Well, I simply use the fact that the limit of integrals on averages on small intervals around that point converges to the mean, converges to, to the center. So to prove that H vanishes on that point, it's sufficient to prove that H has a zero integral in each of these segments. But what is the integral in this segment? The integral on this segment is the integral on this half line minus the integral on this other half line. Because these two integrals are zero, the difference is zero, the integral in the segment is zero, and as an accumulation, you get that the integral, the value of the point is equal to zero. So then H is equal to zero. This was the proof of Sivenko, okay? Very good. On the other hand, if you are a finite element person, right? So if we still are in 1D and we do the comparison with the finite element method, I'm not that surprised that these objects there are dense. Why? What happens when I take sigma to be the ReLU, right? And then I consider a function of the form like this. What is this function? How is the graph of this function going to be in 1D? How is this function going to look? So you have k functions. Each of them is a segment plus linear. So what may happen? Take one point x. Take one point x. What may happen? So maybe x is sitting to the left of some sigmas, and then their values is equal to zero. They don't appear on the sum, and it's only activating some of the sigmas in this sum. But regardless how many sigmas you are activating on this sum, when you are activating them, you are linear. So this is just a combination at any point of linear or zero. So at any point is linear. So the conclusion is, of course, this is a piecewise linear and continuous function. So, oh, but this is like finite elements. When you do P1 finite elements, you get functions exactly of this form. And we know P1 finite elements are dense. You open the book of, I don't know, any classical book in numerical analysis. Very often when I'm looking for something, I take the big book of Quarteroni and Valli, and then you look to the summary, or you go to the original book of Ciarlet on finite element methods. They will tell you P1 finite elements are dense. And you can even give very sharp estimates about approximation rates. You know, for instance, P1 finite elements approximate in H1 to order 1 functions that are in H2, right? So then, of course, this is dense. Why? Well, you see, normally in finite elements, you fix a grid. So finite element theory is built on, building a grid, not necessarily uniform. It can be uniform or non-uniform, right? Of course, if you want to get in finite elements, we know if you want to get first order convergence rate, you need to guarantee that the grid, doesn't have too much distortion, right? You have to assume that all intervals are more or less of the same order, meaning that the ratio between the lengths of all intervals are bounded above and below, right? Okay? So, but in such a case, what finite element says, just make the mesh finer and finer, and this will converge. So there is not only one finite element method. You have one finite element method per grid you choose. And one single choice of the grid, under the condition that the grid becomes finer and finer and finer, suffices to guarantee the convergence of the finite element method. But now, here, there is no grid. Where is the grid here? I didn't talk about grids. So in this method, people will tell you these are methods without grids. We are doing numerical analysis without grids, people will tell you. Well, but in fact, the grid is hidden here because where is the grid? Well, the grid is basically on the switching points of the sigmoid. And where is this sigmoid switching from 0 to being active? This neuron is switching at the point where xj is equal to minus bj divided by aj. So, but what about bj and aj? In this ansatz by Sibenko, bj and aj are free, meaning that in this ansatz, with this ReLU activation function, here you have the union of all the finite element functions for all possible grids. Then, of course, it's dense. You have put together in the same basket all finite element functions for all finite element grids. Of course, this is dense. This is super dense. Now, being super dense is good or is bad? Well, it's not so good. Why? Because there are so many possible functions that there are nearby that you have to choose one. And there is not clearly one that is distinguished among the others, right? It's like if you are sitting on an irrational point and you have to choose a rational that is close to you. Well, there are so many, you know, the rationals are dense around you. So which one you choose is not that clear. So the fact that there is a lot of redundance on this approximation generates a difficulty from the perspective of approximation theory, which one to choose, okay? And this is very much related to the lack of convexity of the functional I was mentioning to you yesterday. Because as I said, in practice, people will not really use the theorem of universal approximation. The theorem of universal approximation is a very good, say, frame to develop this kind of methodologies because density guarantees we have very good chances of success. But the parameters have to be found by minimizing, by training these functionals very much in the spirit of least squares, and the fact that there are so many parameters that are able to interpolate the data, that are able to approximate the function we are looking for, makes typically that these functionals will be full of wells, full of local and global minima. And therefore, it will be hard, you know, to determine what a gradient descent algorithm, stochastic or deterministic, is doing. Okay, very good. Do you have any questions of this? In any case, this is the starting point. As I said, there is still plenty of literature in approximation theory proving variants of these theorems, you know, paying attention to the course of dimensionality to check how, you know, these approximations depend also on the dimension of the space, because as I said, normally here we are representing objects in high dimensional spaces. Therefore, we are working not in 1, 2, or 3 space dimensions as we do in classical mechanics, but in huge dimensions, the image, you know, the space of images or videos. So we have to pay attention to the course of dimensionality, Shannon spaces, Barron spaces, sorry. There are plenty of, you know, studies being carried on this topic from the perspective of functional analysis and approximation theory. But from a more practitioner perspective, this is a theorem that you need to know and gives you a hint of why these methods will likely work, right? So the other day, just after I finished my first class, Professor Ciarlet sent me this affiche of his, the new version of his book in functional analysis. And then I thought it would be good that I show to you. So this is the basis. I mean, functional analysis is the, constitutes the foundation of why all this works, right? But why, right? It doesn't mean that we are proceeding this way. So in particular, you see, finite element theory is linear approximation theory. Why? Because we fix the grid. Sibenko, Wiener, neural networks are nonlinear approximation methodologies. Why? Because these parameters are free. Being free leaves a lot of freedom, a lot of flexibility to approximate all functions, but as I said, makes the problem also hard. Why? Because there are many, many minima. The problem is non-convex and therefore hard to be trained, right? But the foundations are all in functional analysis. Okay, so this is the procedure. And now let's move on. As I said, this is the classical ansatz, the so-called shallow neural networks. Just in one hint, you have to accumulate all these neurons in order to approximate the function. And then if you think on these kind of constructions, this is very hard to do, right? Yesterday I was mentioning the Rubik cube. We all have seen, people solving the Rubik cube. And this is done in a dynamical manner. But this is not what this function is doing. What this function is doing is like accumulating many, many arms and solving the Rubik cube in just one move, combining all these arms. It's like an octopus. An octopus has 8, right? So here, we don't have 8 arms. How many arms do we have here? How many parameters there are? Here there is 1. Here there is d, the dimension, plus 1. So d plus 2 times k. So this, the proper choice of the parameters in this ansatz means that in one shot, you are coordinating all these k times d plus 2 arms, each of them determining one of the coefficients. This is very hard, to have an intuition of. And people thought, why don't we do it gradually? Why, instead of taking a very, shallow neural network, we just do the opposite? So the shallow neural network is a very tall column, right? Then people thought, well, why don't we do residual neural networks? And then it's just the contrary. I just built a time-discrete dynamical system in which, step by step, I just add one neuron. So this is much easier for us to understand, because it means that, there is an input, and then this input is transformed once, twice, 3 times, k times, and when it exits, it should be located on the place indicated by the corresponding output or label. And then, because of this representation as a time-discrete dynamical system, for me, it's much easier to think what I have to do in each step. In each step, I just need to think on how to tune the parameters of one neuron. While here, everything had to be done simultaneously. This is much easier to understand from a mathematical perspective. And then, but when you see this expression, you say, but listen, this is really the Euler discretization, as Professor Zhao was presenting yesterday. This is just the Euler discretization of this differential equation. This differential equation is nice. Sigma is the ReLU. So it's a global ellipsis function. So this, from the perspective of Cauchy problems, is well posed. You give me an initial datum, I will have a trajectory. But what about the coefficients W, A, and B? Initially, there were very many static. Now there are very many dynamic. But when you make the mesh finer and finer on time, what you get here is actually functions W, A, and B that depends continuously on time. Oh, but this is exactly what control theory does, right? You turn on the car and then you gear the car, to bring it from origin to destination. This is time dynamic control. So once you think in this model, you realize that then supervised learning becomes the same as a classical control problem, except that here, the model is always the same. So you see the advantage of machine learning from this perspective of control is that everything is about controlling the system, but it's not like in control theory where there are many systems, because you have to deal with all systems of nature. You have to deal with wave equations, with heat equations, with the Schrodinger equations, with nonlinear oscillators, with Lotka-Volterra equations, with transport equations, with stochastic differential equations. Here is always the same equation. Why is that? Well, because here we have adopted a purely synthetic, artificial perspective to modeling. We are not modeling according to the first principles of mechanics or physics. We are just modeling out of data. And therefore, in particular, when dealing with this data, we don't care what the application field is going to be. So you see, we are led to this very simple system and the analysis of the control of this system. There is, however, a difference. In classical control theory, you take one car and you go from origin to destination. But here in machine learning, we want to classify all the data set. All the data sets simultaneously has to be mapped from input to output to labels. So it means that, it's true that the problem looks particularly simple, given that we always have the same activation function, the same nonlinearity. It's just the ReLU. It's very simple. Nothing sophisticated about the ReLU. But on the other hand, we are asking for this control problem to do much more than we usually request. Because normally we request in control theory, control one trajectory and then the other and then the other. Here, all trajectories have to be controlled simultaneously. So that in particular, when you are given this data set, in which clearly, healthy individuals and ill individuals are all mixed up, you have to be able to classify this data set so that blues go to one side and reds go to the other, right? Like, players of a soccer match, when they get to the field, there are 22 players, right? But then before the match starts, the 11 blue and the 11 red has to be in two differentiated halves of the stadium. Okay? Very good. Now, something that has contributed a lot to the success of large language models is a very smart way of, putting labels. I think Professor Zhao mentioned that yesterday too. Is the next token prediction idea. Actually, if you think on how, for instance, these tools like ChatGPT or DeepSeek or even before DeepL, how they do translate a text from Chinese to English or from English to Chinese. I mean, when I was, before ChatGPT and these large language models, when I was using those tools, I was surprised how efficient they were. And then people will tell you, yes, but they use artificial intelligence. Well, but artificial intelligence, how? What does it mean? How do you train these models? It means that you take plenty of text in Chinese and then, the corresponding translations, and then the computer will learn all these translations to then translate new text, or how is this done? In particular, in this case, even within a given language, so assume you are just dealing with, say, text in Chinese, and you want the computer to learn how to write in Chinese, so that when you say to the computer, please write down a letter to my dean asking for a grant to, to attend an international conference, and then boom, you get in, 2 seconds, you get a 1 full page of letter, so well written that the dean will almost be unable to say no, right? I mean, you write so well, you are so kind that I have to say yes. How does the machine learn doing this? Where are the labels? I can see that there are many inputs, right? I can take words, I can take sense of words, I can take sentences, I can take paragraphs, but to me, all this is in the X side, is the input. Where is the label? They had a great idea. You give me a text, and then you can build out of this set, this text, you can build inputs and outputs. Is the next token prediction idea. So the idea is, given a text, of course, the number of words is not maybe the same. So this can be characters, this can be syllabs, this can be words. It depends also on the language in which you are writing. But the idea is that whenever you choose a written unit, a token, they call it token, right? You have a next token. Therefore, you can, whenever you take one, the next is the corresponding label. So each 2 words, consecutive words, means that you are generating a pair of input and output. You can also take 2 words as input and then associate to it the 3rd word. So you see then that in a text, there is plenty of information in which not only you have many, many inputs, but you also have many, many outputs. You have many, many labels. And this allows you to build, your dictionary on which you will learn, and you will be able to apply these ideas. So you see, this was a great contribution, is to understand that very often, even if you think that there is no information on the given data set, because you only see the X, well, maybe the L is hidden there, but you have to discover it. And the discovery of the L here was through this next token prediction. It's like here, right? So normally when you go to a lecture room, well, in principle, I only see individuals. I only see 25. One is sleeping, for instance. The other are awake. Is there information on this group? Yes, often there is, because people, for instance, from the same group with the same thesis advisor or friends, maybe often they sit together, right? But this information has to be extracted. It's not given on an Excel table. You need to figure out how the information is organized so to be able to extract the labels. This is something that applies to, to languages very naturally. Maybe it doesn't apply on the, I don't know, when you go to the subway station and the subway is very crowded, so maybe there is no connection, right, between individuals that are one next to the other because, on the peak hours, maybe very often people just get alone in the metro and then they gather there. So there are other scenarios in which probably this doesn't really mean anything. But in large language model, it does. And this is how, one of the keys of the success of large language models was to have this great idea of associating labels to inputs according to this next token prediction rule. As I said before, all this requires a lot of statistical sampling. You will never do things very well if the data set is not well prepared. So when you see explanations of how the data set for learning in ChatGPT or DCN is prepared, this is extremely sophisticated, right? There is a lot of engineering, a lot of know-how of image processing and text processing to be able to prepare a data set so that these more or less naive mathematical ideas can succeed on building a neural network model that really learns out of the data set. You need a lot of structure, a lot of cleaning, very much like in classical, say, numerical PDE basis, reduced basis methods and so on, in order to succeed with these strategies. Okay? Actually, I think one of the contributions of DeepSeek with respect to classical ChatGPT was to adopt, say, more multi-scale perspective to learning. Right? Instead of learning everything, simultaneously, try to classify the information better and then learn gradually, right? Which also corresponds to the way we see, right? So when I watch the wall, I see bands, I see blue, but then it's only when I get closer to the blue that I will see, for instance, the rugosity of the tissue, right? So we have our human brain perceives in a multi-scale manner. We learn in a multi-scale manner. This is why we have to work on a topic again and again. In a first reading, maybe we grasp the main ideas, the main results, but then we need to get more into the details in order to learn the proofs and then do the exercises, right? So we have a multi-scale way of perceiving reality and learning. The same idea was implemented successfully by DeepSeek. And in this way, you do better by using less computational resources. Okay, I mentioned control as a way of understanding machine learning. Well, there is not a single way of describing a mathematical breakthrough or a mathematical development, right? Actually, this book that I strongly recommend for mathematicians by Ernst Heider and Wiener presents calculus, classical calculus, but from a historical perspective. And the preface to the book says the following. Most of high school students, when they go to the math faculty to do the bachelor in math, they enroll the university to do the undergrad studies in mathematics, is because they like calculus, they like numbers, they like, I don't know, combinatorics or, or integrals or calculus. They have some, since they are childs often, they have some affinities towards numbers, which are, the typical animals you encounter in mathematics, right? So mathematics is a jungle full of numbers. So you like numbers, then you study mathematics. And then they get to university, and they are shocked because professors start teaching very abstract things that they can hardly understand, right? So this is what precisely this book says. So normally you get to the university and then the professors start talking about logics, sets, mappings. They spend 1 week on doing the Dedekind cuts to prove the existence of real numbers and the real line. But the real line, I just draw it, right? So why do I need to spend 1 week building the real line? I can just draw it. And then they start with epsilon, delta, right? With epsilon and delta, then they define the concept of a limit, and then continuity, and then differentiability, and only in the end, in May or so, they do very quickly integration theory. First Riemann, then Lebesgue, and all these just to compute areas. But areas is clear, right? What an area is. We all understand what the surface of a wall or the volume of a three-dimensional body is. So this book precisely says, listen, and then many students have difficulties to follow this program because the program is built in a time reversal manner. Actually, historically, mathematics was built first to solve very simple problems, like in Aristotle's time, right? At that time, there was, Protagoras of Abdera. He was a very smart guy. He knew about everything, and he was a nomad. He was traveling from one village to another, solving all issues, right? All conflicts. And, sometimes Protagoras of Abdera, he had to develop a very difficult task. That was, someone passed away in the family, parents passed away in the family, and the family owned a very complicated piece of land. And then the family had 7 kids, and Protagoras of Abdera was the one who had to split the domain into 7 pieces of more or less the same area, like in domain decomposition. Oh, and people were very tricky because then they were, they were checking whether, my piece of land is better or bigger than the other, right? So mathematics was started to deal with precisely the problems of integration theory. And it took a long time. It took a long time, from the most classical developments by Kepler and Fermat, Newton, Leibniz, Cauchy, Weierstrass, Cantor, Dedekind, and all the functional analysis that came in the 20th century. Of course, students have difficulties to understand the way we teach calculus, because nowadays, we start from here, and we try to go backwards. But students go to university because they like this kind of classical mathematics. Okay, so this is just to say that there are many ways of telling a mathematical history. What I'm saying here is not the truth, it's not how things happened, but it's a way we can interpret a posteriori all this success of machine learning from our applied mathematics know-how to understand it better and to make it coherent, okay? And in that sense, control theory helps. So control theory is already built in nature, right? So this is a good example. Let me see if I can, yeah. Okay, so this is just to say, listen, if you have to do simultaneous control, if you have to build this neural network system or this neural differential equation that I wrote on the top, right? Instead of using machine learning, you can hire these border collies, and they know how to split ducks according to the colors, right? So you see, they had this strategy of, getting close and then away like an accordion oscillatory, zigzagging, so to force somehow ducks to split according to an interface in which white will be to one side and black to the other. As I said, as in a soccer game in which the 2 teams get split before the game starts, okay? So now, this is definitely one of the applications of control theory, to human and animal behavior is collective dynamics. I mean, you have, online fantastic videos. These are huge, flock of sheep, I think in New Zealand or in Australia, where several dogs coordinate. And nowadays, this is also done with drones, right? So sometimes drones replace dogs in order to herd huge flock of sheep. So mathematically, we can also do it. So let me show you how you can build a mathematical model that is able to herd a flock of sheep. Now, there is no music this time, and there is only one dog, right? The objective here is different. It's not splitting the herd of sheep into two, but it's just bringing all sheep to the gate, right? So when you see the algorithm, I think you understand what the algorithm is doing, right? What is the dog doing? The dog is in red. The sheep are in yellow. And you see there is a little dot here, a reference dot here. There was a dot, which is the destination of the herd. So what is the dog doing, in your opinion? What is the dog doing? You see, the dog starts running, and then he places himself behind the flock of sheep. And then at any time, he's being aligned with the destination. As soon as the sheep meet this obstacle, they start rotating, and then the dog rotates as well. And then, spontaneously, by just the fact that the dog is behind, if I am afraid of dogs, if I have a dog behind, what do? I walk in the opposite direction. And when the dog, shifts to the left, I will move to the right. I'm just always trying to avoid the proximity of the dog. And this is precisely the force that pushes spontaneously just by placing the dog behind the flock of sheep. This is the force, the repulsion instinct of sheep towards the proximity of the dog that makes that this dog can control the herd of sheep. Let me show you another example. This is a competition in Basque Country where I am from. There are competitions of shepherd dogs. Let me give you another example. Okay, so you see, what do you observe? First, sheep like to be together. There is a lot of viscosity. There is a lot of cohesion. So in the end, sheep, they almost behave like a big elephant, right? There is, though, some tendency to dispersion. Individual sheep, if they are a bit nervous, they can escape the flock. So the dog has to be reactive to avoid this dispersion. So the first goal is to keep this flock of sheep very, very, coherent. Because then they move all together. And if they move all together, the dog has to basically do what I have shown in the previous numerical simulation. Just be behind, so to push the herd, the flock in the corresponding destination. And this is why the shepherd, most of the time, actually he's talking in Basque, but most of the time, the shepherd is saying to the dog, be quiet, be quiet. Is just refraining the dog from the instinct of the dog of running fast toward the sheep. So just a very little action of the dog suffices for the sheep to be very reactive and then oscillate, zigzag in the corresponding direction. So this is control, simultaneous control. You agree with me that we are doing simultaneous control, right? Because one single dog is not only herding one single sheep from the origin to the destination, which is crossing this gate, clearly. This gate was the destination, but all of them simultaneously are being driven to the destination. So this is the idea of simultaneous or ensemble control. Now, what we have to do in the context of machine learning is do the same, but now, with all the data set we have, and the control being the parameters of this neural network that has to be designed so that this dynamical system guarantees that all inputs get to the corresponding output or label. Dynamical systems, like, in these graphics where the dynamics of sheep is modeled by the red dots, while the dynamics of the dogs, in this case, 2 dogs, are designed by the blue dots. And in order to succeed on controlling such sensible dynamical systems, we have to apply the so-called model predictive control strategy, right? So what is model predictive control? Well, model predictive control, the words already tell you, right? So is that when you control a system, you have an idea of how the system is evolving, but you don't have a full understanding of it, right? Even if you write down the ordinary differential equation or the partial differential equation for the dynamics of the process you are handling, there is always uncertainty on the system. There are parameters that you don't know how to calibrate perfectly. Right? So you learn while you are really controlling the system. For instance, if you are offered a new telephone, right, for your birthday, what do? Of course, the telephone you have, in internet, there will be maybe 500 pages written about all the possibilities that this new telephone offers. Do you read these 500 pages? No. You just take the telephone, you turn it on, and you start operating. And by operating, you learn how it works. By operating, you see, now, there is a new app. Now it's easier because there is face recognition. Now it does this and that the previous version was not doing. Oh, now the photo program allows me to generate videos and, do all kind of tricks. So you learn by doing. So this is model predictive control. You predict what the model is and you control it. But then you observe that, maybe what I did was not perfect because my understanding of the system was not perfect. In the next iteration, I improve. And this is what we humans do all the time. We don't need to take courses in model predictive control to do model predictive control. For instance, when you use the Maps app in your telephone, and yeah, I have to go from here to the hotel. Okay, if I ask, go here, from here to the hotel, you know, the map will tell me, go through the north gate, exit campus on the north gate. Then I follow the map, and I get to the north gate. Oh, but the north gate is closed. The north gate is closed. This is a local decision because they are doing some construction. But of course, the map app doesn't know. So I was acting on the system. I was controlling by walking in this direction under the premise that the geodesic was going through the north gate. But I didn't have complete information. I was missing the key information that the north gate is closed. So if the north gate is closed, what do? Well, I can climb the wall and jump the gate, or maybe I check where is the other gate. Oh, the other gate is to the east. So I have to walk to the east, exit to the east, and then turn around the campus to get to the north. This is model predictive control. And this is something that, you know, already was invented when, you know, the first Apollo mission. They had to send the rocket from Earth to the moon. It's a very long trajectory, right? Of course, there was a pre-computation of how, you know, the rocket has to be operated to bring it from Earth to the moon. But this had to be refreshed regularly according to measurements of the actual positioning of the rocket at any time. Because obviously, the rocket didn't follow, you know, continuously the parabolic trajectory that was initially designed. So in practice, right, we aim to take the geodesic path, but in practice we are unable to realize exactly the geodesic path. What do? We just do a zigzagging around the geodesic path. And every time you switch from one direction to the next, this is when you are refreshing your understanding of the model. You learn more about the model, and this allows you to switch. This, of course, also is extremely interesting when, you know, you are dealing with processes that are subject to, you know, unexpected random inputs or fluctuations, right? It's like, well, I mean, like today, well, I was planning to go to the hotel walking after, you know, the classes in the afternoon. Oh, but maybe if there is a very heavy rain, I didn't anticipate now because now it's sunny. But who knows, maybe at 6 p.m. it's raining very heavily. Then I was planning to go walking, but I will not walk. I will take a taxi because I don't want to get wet. So you see, there are, you know, unexpected events can also force you to switch from one control strategy to another. And you need to have flexibility for doing this. When you are operating a system, you need to have the freedom to adapt your control strategy to the changing circumstances, right? And this is what model predictive control does, okay? And this is an idea that is also very much built in the context of machine learning, specifically when you are dealing with, you know, the learning of dynamic data. If data are static, you see the picture, you can learn once forever. But when the data are dynamic, like videos, right, you need to, you know, have the possibility of adapting the parameters of your neural network to better track the dynamical system under consideration. And this is very much, you know, classical control theory. This is, you know, a slide just to show that, you know, how things work, how things work in this case, where, you know, in order to build, we have a couple of papers on this topic, in order to build this model in which you can show how, you know, dogs are controlling a flock of sheep and so on. This, you know, analytically is complex, but can be done. You have to build an ordinary differential equation for each sheep, an ordinary differential equation for each dog. You have to define the interactions between sheep with sheep and sheep with dog, and then you have to let, the shepherd to decide about the dynamics of the dog, so to control, to give instructions to the dog. You have to solve an optimization problem very much like in the training of neural networks to guarantee that all sheep, all XKs get to the final destination, again, by solving an optimization problem. This, of course, when the number of sheep is very heavy, becomes a quite high-dimensional problem of collective dynamics. And this is why, in order to better implement it, we apply random batch methods, which basically is domain decomposition plus, stochastic splitting. And as I said, we always employ also model predictive control simply to be prepared to the possible unexpected events and uncertainties of the system, okay? This is how control theory deals with these important problems of collective dynamics in animal and human behavior, right? And why this works? So why this works, or at least why it may work if you do things properly. So this was a fundamental contribution. So first, the same Norbert Wiener that wrote his celebrated paper on Tauberian theorems, that was the first paper on nonlinear approximation theory using the Gaussian function as activation function. He was the one who wrote this book on cybernetics, The Science of Control and Communication in Animals and Machines. And you say, well, I mean, cybernetics could be also the definition here. This definition could be very much the definition of artificial intelligence. So after all, what are we trying to do? We are trying to build machines that operate like animals, in particular as humans, right? And this is what we have succeeded to do to a large extent, right? So we have machines now that are able to translate a text from one language to another, something that was taking a lot of time to the human, now is done very fast by the machines. We have machines that can compute a lot of, solve very big computations on a time that for us will take forever. Now the machine can do it very fast. So basically the machine is able to do things. I mean, the machine can do a drawing. The machine can write a poem. Maybe then you say, well, the poem is not that good. Well, but it can. Okay, it can write a letter to the dead. So we are building machines that are able to do the task traditionally allocated to humans. And then the second idea on this in Norbert Wiener is that you need control and communication. So you need sensors and actuators. So the air conditioning system cannot work if there is not a sensor, a thermometer. I mean, the machine needs to know what is the temperature in the room. If you don't know what the temperature in the room is, you will never be able to regulate the temperature so that it is, 23 degrees. But you also need an actuator, because you need to inject cool air if needed in order to make temperature decrease from present temperature to the goal temperature of 23. You need sensors and actuators. You need communication and control. But this is the same in machine learning. You need data. As I said before, if there is no data, then it's unsupervised learning. This is a very, heuristic splitting. There is no guarantee that this will have anything to do with your application in mind. You need data, communication, and then control. You need training. You need to train. You need to prepare, compute the coefficients so that the system does the job. So you see that here in this concept of cybernetics and this very definition of cybernetics with two, say, pairs, right? Communication and control on one hand, and animals and machines in the other, you really see the roots, the foundations of what we understand today as being artificial intelligence or machine learning. Then it took 10 years until This theorem was clearly formulated by Kalman. This was a very seminal contribution in control theory because also the notation and the frame was very clearly established, right? It's like Cauchy problems for ordinary or partial differential equations. So what did Cauchy say? Cauchy said, well, stop computing explicit solutions of ODEs and PDEs. Of course, you can do that in many cases, right? We have the explicit solution of the harmonic oscillator. We have the explicit solution of the heat equation of the, there are many, many equations we can solve explicitly. That was the trend in the old times. And then Cauchy said, stop. You don't need to do this. What you really need to do is to write down your dynamical system, allocate initial data, and then try to understand whether there is a unique solution for this problem and how this evolves in time. This is a more abstract concept of dynamical system, not simply oriented towards computing an explicit solution. So here, in control, it was the same. Kalman said, you can consider in one shot all these classes of linear system, x prime equal ax, And this can be, A is a matrix, right? X is the state, it's a vector of dimension D. So this can be, for instance, a heat equation, partial differential equation, discretized in finite elements. You get this. But can also be the WeChat network of this group of people, where A is simply representing the connectivity matrix. That, as I said yesterday, maybe it's not full. I only have the WeChat number, I think, of 5 people here. Right? So the matrix A is not full. But this doesn't mean that we are not connected, all of us, through the inner structure of the network. This is like the small world paradox, right? So you think on, I don't know, someone, very distinguished person, and you say, oh, I never met this person, I will probably never meet this person. Yes, but maybe in 3-4 iterations you are done, you get there. This is like the concept of Erdős number in mathematics, right? So each of us has an Erdős number, and you can check the Erdős number in the MathCNet, right? Have you ever done this? Okay. So you can check yourself. You write down Erdős number, and you can see what your Erdős number is. Paul Erdős was this celebrated Hungarian mathematician, right? He wrote many, many articles, and then each of us has an Erdős number. So probably everyone here that has written an article has at most Erdős number 3 or 4. What is your Erdős number?
2 or 3.
Yeah, it's very small, right? Because, everyone that has written an article with Erdős has Erdős number 1. But he wrote hundreds of articles with hundreds of people. All of them have Erdős number 1. I have Erdős number 2 because I wrote once an article with a person that wrote an article with Erdős. And then UBL has at most Erdős number 3, at most. Because we have joint article, and I have Erdős number 2. Your Erdős number is less or equal than 3. You have to check. Because when you open this web page and you write your name, then the machine will tell you what is your Erdős number. It could be that, UBL's Erdős number is 3 at most, because he has a paper with me. But if he wrote a paper with someone else who has Erdős number 1, then he has Erdős number 2. This is the small world paradox, okay? So that was the idea of Kalman. He said, let us consider this system. I don't mind what is the origin. It can be a system coming from a social network. It can be a discretization of a partial differential equation. It can be a finite dimensional dynamical system. I don't know, Lotka-Volterra equation in population dynamics, can be an SRI model in infectious diseases, it can be a financial market model tracking the values of the different assets on the market, on the stocks, and so on. It doesn't really matter. The dynamical system is modeled by this matrix A. This is the free dynamics. But now, this dynamics is controlled. There is an input. There are influencers that are injecting information into the system. There is air conditioning. There are people that are investing money in the stock markets. There are vaccines in the, in the infectious disease. So these are the external controls that are there in order to modify the dynamics of the system and drive the system to the destination. There are dogs that are influencing the dynamics of the ship, right? These are the controls. And the controls are acting through the system through, the matrix B. So in the extreme case, you are in a situation where X, the vector, has D components. Then when you write X prime equal AX, this is a matrix in dimension D times D. But the extreme case will be the case where there is only one control, one single dog to control all the flock of sheep. One only, president for the whole university making all the decisions. One single control. Can one single control a system? Well, in that case, you see the matrix B, in this case, is just a vector. And this vector is telling you how much, the decision, the input of this single control is affecting all the components of the system. It can be that many of them are zero. Because, many of us, we don't talk to the president of the university. We don't talk. We never met the president of the university. We just talk to our colleagues. We may talk only to the chairman of the department. Yes, but the chairman talks to the dean, and the dean talks to the president. So the question is, there is some intrinsic connection within the system that is modeled through the matrix A. There is an intrinsic way in which the input of the control is distributed along the different components of the system, and all this is mixed along time. Time evolution generates mixing. Question, is this system controllable? And what does it mean controllable? It means that give me any initial datum, give me any final datum, can I control the system from the initial position to the target? And the answer by Kalman was, yes, if and only if, when you check this rank is full. Okay, very simple linear algebra response. You compute this rank, and if the rank is full, then the system is controllable. If the rank is not full, the system is non-controllable. There are non-controllable components of the system. For instance, my own body, is it controllable? Well, it's controllable on the plane, right? I want to go from here to there, then I can. But I am not controllable on 3D. If I were considering myself as an object embedded in 3 space dimensions and I compute the rank, I will not get 3. I will get here 2, which means one direction is non-controllable, right? It's like if you are dealing with a group of individuals, and this group of individuals is very interconnected, right? But then there is an individual here that is isolated. Well, if this individual is isolated, the control U that is acting onto the core of the system represented by this cluster will be controllable, but this isolated individual not, because the action of U will not get over there. So this is typically, you know, the interest of this result is not only that tells you whether a system is controllable or not, but actually when you compute this rank, even if the rank gives you a pessimistic output in the sense that it tells you, oh, the system is not controllable, it will also tell you how many directions you are missing. Okay? Now, think on solving this exercise yourself. So take this matrix. We are here 25. So the matrix A is going to be 25 times 25. You have to check whether this rank condition is fulfilled. Well, this will be a very heavy computation, right? Because you have to take the matrix A, and you have to compute 24 powers of A, right? It's already very heavy. You take a matrix 25 times 25, you multiply by itself, get a square again and again. It's very painful. And you have to multiply by the matrix B, and you have to check whether the rank is D. Of course, when you take the MATLAB, for instance, toolbox in control, there is a command to compute the Kalman rank. This is the very first thing you do whenever you have a control system. When you open the toolbox of control, then you would like to know how controllable the system is, and then the simplest criterion is to compute the, the rank. But I don't know how big the matrices you can deal with MATLAB will be. Certainly they are limited. Actually, one of the trends in, for instance, one of the projects that was recently developed by DeepMind using artificial intelligence was to develop new methodologies to compute products of big matrices. Right? Why? Because, scientific computing, in the end, everything builds into very elementary operations like solving linear systems, multiplying matrices, but you have to do that very frequently. And of course, with the modern applications of artificial intelligence, you have to do it for very large systems. So multiplying big matrices faster has become something important. Okay? So now, this is something we learn in the driving school, right? So I think in China you need what? 4 exams to get the driving permit, right? I think in Europe you need only 2, but I mean it's still very expensive. You need to take like 20 lessons to learn how to drive, and every lesson is very expensive. So you need to spend at least 2,000 or 3,000 euros to get the driving permit in Europe, right? So now this is the exercise. We are, of course, driving the white car. And, oh, there is a parking lot. We are very happy because there is a free parking lot. And we have to park the car. So how do we park the car? So, Senan, how will you park this car? You have a driving permit?
Yes, I do.
Okay. And you drive regularly?
Yes.
Okay, so you know how to do it. So what we will do?
So there are 2 ways.
Yeah?
If you're having automatic car, you just press a button. Or you go straight ahead and try to tilt the wheels, like you sliding for some time, and to some extent you turn the wheels again to adjust the direction.
That's it. So yeah, I mean, the first thing is that we can try to do it forward, but it's not gonna work. So we know that if I try to park, say, oh, let me just occupy this space, moving forward, I will not be able to do it. If I try to park forward, I will get the car into some diagonal situation, and this will not improve. So first observation is, I cannot park just by moving forward. Oh, sorry. In order to park, I need to combine forward and backward motion. And this is what actually the optimal parking is. So this is the optimal parking computed by the computer by solving an optimal control problem. Of course, a driver normally doesn't do it that well. A professional driver will do something very close to this, but probably most of us will have difficulties to reproduce such a perfect parking strategy, okay? So let me show you again. So this is where we are. We know that forward parking will not work. Then somehow the strategy is to move forward, stop, then turn the wheels, and then move backward in order to enter backwards diagonally. But then because we have to gain the horizontal alignment with the, with the pedestrian path, we have to rotate the wheels in the opposite direction, right? And this is what actually the optimal parking does. Move forward, stop, move forward, stop, angle, backwards, stop, switch of angle, backwards, perfect alignment, and then just move forward to be placed in the center of the empty space. So why do you think after moving forward, the car stops? Why do we stop? Because you see, from the perspective of control, this is something like, so from the perspective of control, so the U was, say, 1 for a while. Then when we stop, the control, right? So here is 1, here is 0. But the system continues evolving. So the fact that you are doing nothing with the control, it doesn't mean that nothing happens, because the system continues evolution. So why here, after moving forward, we stop? We move forward, we stop, and then there are these yellow lines appearing. What does it mean? It means that we are taking measurements. We are taking measurements, and these measurements allows us to move forward, and then we take measurements again, and this information we are gaining, right, allows us to compute optimally the controls. So whenever you stop, you watch, and when you watch, you understand better the configuration of the system, and this allows you to, right? This is critical, say, time instances in which you are gaining information of the system, and this allows you to better control it, okay? So these are the classical ideas in control theory that, as I said, they started with this celebrated paper by Lord Maxwell on the governor engine, and there are many books. In particular, there is this book by Eduardo Sontag, you can download it freely from the Springer webpage, where you will find, an introduction to this classical context in control theory, right? So then our viewpoint is, listen, control and machine learning are very, very close fields. And we see that. So this is the video simulation of the 4 dogs controlling a flock of sheep. And the second one, if it comes, is the video of a deep neural network classifying a data set according to the labels. So both videos look very much the same. Both videos seem to be like simultaneous control processes for a collective particle system, particles interacting in some way. But actually, this is not the case. So this is control theory. There are 4 dogs, while here there is no control. Here, data seem to evolve spontaneously. This is why people used to say, well, this is machine learning, but has nothing to do with control. But in fact, it does. Why? Because we have observed that in order for the deep neural network, in order to be able to perform successfully this classification task, you have to learn the coefficients. And learning the coefficients is the same as computing the controls. So the time-dependent parameters of our deep neural network are actually controls of this system, except that we don't draw them because there will be too many, right? In particular, if we were considering this neural differential equation, I will have one parameter for WT, D parameters for A depending on T, and one parameter for B of T. There will be D plus 2 controls. If the dimension D is large, this will mean many controls. So we don't draw them. We are not interested on what the values are, but they are extremely important because the neural network only succeeds if you are able to train it properly, okay? So then how does it work in practice? Well, for instance, you have to solve this problem. You want to build a neural network that will classify trash. So you have 4 containers, yellow for plastic, green for glass, blue for paper, and gray for organic. So you have to build a machine, a robot that will classify trash. You can hire people doing this. Yes, but people don't like to work on this, right? So this is dirty work. So we prefer a robot that will be able to do this. I mean, you have to, embed a program on the robot. And a program is what? It's a function. So it's a function that understands, oh, if this is plastic, it has to go to yellow. If this is glass, it has to go to green, and so on. How do you build this function? Well, you do it by supervised learning. You take a number of items that represent properly, and this is the sampling. You need to sample well the family of objects made of plastic, and this is why you have a bottle, you have a glass, you have a bag, you have bottles of different sizes, glasses of different shapes and different colors, because you want the machine to learn which objects are likely to be plastic. The same for the other 4 objects, right? So for instance, in organic, well, you have to teach machine bread and cheese and tomato and fish. Very good. So now, and these are the labels, different destinations. So once you have your data set, how can I make this to become a problem of learning a function from one space to another? Well, you just take pictures. So each of these objects becomes an object in our Euclidean space just by taking pictures. And then what is the dimension D? Well, the dimension D depends on the resolution of the image, right? But for us, that will be an automatic way of representing objects into, the Euclidean space, just by taking pictures. Of course, in practice, there is a lot of math that has to be developed in order to do this. For instance, you see, one of the typical topics when people are dealing with using machine learning for solving partial differential equations, how do the classical papers in PDEs start? What is the first sentence in every classical PDE paper? The first sentence is, let omega be a bounded domain. Yeah, let omega be a bounded domain. Yes, but omega is a bounded domain. A bounded domain can be of very many many different shapes. How does the computer learn about the shapes? How do you represent domains in the Euclidean space in a way that you can encode in a machine learning program? That's not so easy. Okay, you need somehow parametrizations of domains, right? The same as when you develop finite element theory, you need to triangulate domains. Of course, for us, this is done automatically, right? The program does, the automatic triangulation of the domain. Nobody cares how the triangulation was computed, but someone did it before us. Because the fact is that when you open a finite element solver and you define the domain, then you click and the solver will generate the triangulation. Someone has done some pre-processing that, leads you to a reasonable triangulation of every specific domain, somehow adapted to the geometric features and the topological features of that domain, okay? So that's not that easy. But we can assume that this is done just by taking pictures. Okay, and then once this is done, you say, you know, this class of data has to go to yellow, this class of data has to go to green, and so on. Once you do this, you solve this optimization problem. As I have said, you train this neural differential equation. I call it neural differential equation. Why? Because it's just a differential equation, but sigma is inspired. It's just the ReLU is inspired on neural network architectures. I solve this optimization problem, and it works. I see that yellow go with yellow, purple go with purple, and green go with green, right? So in this case, 3 different colors. So this is the success of control, and why control suffices to explain, you know, the success of machine learning for solving these supervised learning problems. Okay, very good. Now, the next question that I would like to explain today is, well, fine. So this seems to work computationally. We have also seen Kalman, but I mean, is Kalman sufficient in this setting? Well, certainly not. Kalman result was valid for linear systems, and this is a nonlinear system. This is a nonlinear system. And actually, we made emphasis on making nonlinear because, you know, neural networks are successful because they are nonlinear, because they, you know, they have the capacity of, you know, switching from on to off and vice versa. So linear control theory is not sufficient to understand this. So why this is true? Well, this is presented in this Cyan review paper we published a couple of years ago with Domènec Ruiz-Vallet, who was formerly in our team, and now soon will be integrated at the University of Barcelona. So in that paper, we show, the paper says, right, the statement is certainly a bit longer to be formulated rigorously, but the theorem says, yes, we can, right? So yes, you can understand easily that this architecture in dimension 2 or higher, not in dimension 1, in dimension 1 you cannot classify data. Why? Because data cannot cross, right? They will collide. But as soon as you are in dimension 2 or higher, you can easily classify data, right? As we have seen, you know, dogs and ducks, or dogs and sheep. You can definitely classify data following these very ideas. And what is the proof? The proof is very much like in the Rubik cube. So what is the link between, you know, the Rubik cube and the proof we do in that paper for the fact that these neural differential equations are able to classify data? Let's see. Let's check what this ODE is doing, okay? So recall that X is representing each of the objects in dimension D. These objects are evolving in dimension D according to the trajectories of this neural differential equation, right? And they are supposed to be controlled simultaneously from their original destination to the corresponding labels or baskets, okay? Very good. Take one of these objects, X, at any time, X of t, okay? Now, let's try to understand in which direction this object is evolving. Let's see. Take X of t, and then let's try to determine in which direction it is evolving. So I have to compute X prime. So X prime is W, is a scalar, right? Sorry, a vector in this case, times sigma, a scalar. But what is sigma? Well, sigma is the ReLU. It's either negative, and then sigma is 0. The argument is either negative, and then sigma is 0, or the argument is positive, and then sigma is linear. But now, when does A dot X plus B be negative or positive? Well, it simply depends on how the point X is collocated with respect to the hyperplane A dot X plus B equals 0. So at any time, whenever you choose A and B, you are choosing a hyperplane. And then whenever x is to one side, sigma is equal to 0. Whenever x is on the other side, sigma is linear. And then W is just the direction of the wind. So in this control system, basically what you are doing is with one hand, you are cutting a space into two halves. And with the other hand, you are pushing the active subspace in the direction of the W. So you are coordinating the two controls. One control is you cut, and the other one is you push. But at any time, because this is a recurrent system, this is a time dynamical system, you can think on it as time continuous or time discrete, doesn't matter. You can concatenate in an inductive manner, in an iterative manner, these actions. Cut and push, cut and push, cut and push. And this is precisely what we do for the Rubik Cube. We hold the Rubik Cube with one hand, half of the cube is frozen, while the other one rotates. Half is frozen, the other one rotates. And from one action to the next, you choose different directions. Different halves are frozen, different directions of rotation. Okay? And this is what happens, and this is what explains the success. So I conclude with this slide where I show you very easily how, in this case, we can succeed. So this is a very toy example in which we have 9 data, 3 blue, 3 green, 3 red, that we have to classify in the corresponding baskets. The blue should go to the blue, the green should go to the green, the red should go to the red. We check, oh, they are all well placed except for one. One is badly collocated. This blue is in the green basket. So we have to take this blue from the green basket and bring it to the blue basket there. Okay? But we have to do it keeping the green in the green, the red in the red, and the blue in the blue, of course. Right? So how do we do that? Now, think that these are initial data for this neural differential equation in 2 space dimensions, and that I can concatenate motions in which I cut a space in 2 halves, one moves and the other doesn't. What is a smart control strategy, inductive, iterative, that allows me to solve this problem? Well, this is a good solution. Cut vertically, the left is frozen, right goes up. Then cut horizontally, down is frozen, left, up moves left. Okay? So I do it again. So you see, the idea is the following. These two are horizontally aligned. But if I cut vertically and I push this a little bit, this horizontal alignment will be gone. And therefore, this blue will be isolated on a horizontal strip. If I cut horizontally up and down, and I move the upper part and the down part to the left, this blue will be isolated here to the right. And once the blue is isolated to the right, just one motion will suffice. So you agree with me that if this blue were here, if this blue, instead of being there, were here, it would be very easy to push to up. I will just need to cut vertically here and push the right up. That's all. I need just one motion if the blue is to the right of all others. So I just used 3 motions. The first 3 initial motions are just to make sure that the blue is to the right of all others. And for this, I need to push, all others to the left. If I start doing it now horizontally, I can cut here and push this to the left. I can cut horizontally and push this to the left, but this one will always be to the right of the blue. In order to avoid this, what I do is I do a vertical cut, I push, and now in 2 iterations, the blue is to the right, This is 3 iterations, and the last one is just to move the blue up. So this is how it works. One motion. Now 2 motions to move every other element to the left. And once the blue is isolated to the right, 1 motion to just move it up. Okay, thank you for your attention. We continue tomorrow. Thank you.